Okay, so we've got a function f which maps g to h, and I want to show that we have got a group operation on h. Let me just remind you what we're doing. We're mapping g, which is this square here. All we're going to do is map it to the coset that it lies in. That's all we're going to do. We're going to map an element here to the coset that it's sitting in. It's just an inclusion map. I think that's the word for it anyway. So x is mapped to nx, and of course y is mapped to ny. Well, that's great. But what I need to do now, we've got f which maps g to h. I'm going to write nx ny equals nxy. So what I'm doing here is I'm defining this little dot here, which is my group operation of h. I'm just going to write it as a dot. This operation in here is a group operation in g, but I'll write the h1 as a dot. Now I need to show that this is well defined. Let me just draw the picture again. There's g, here's my cosets. That's n, nx, ny, nz, and n, I don't know, t. So the problem is I need to show that this is defined, or well defined. In particular, it is an operation, or dot here is an operation on the cosets, and it should not matter which element you choose. Okay, so I've got my little diagram here. I might have chosen there's x, and there might be x dash. So they're both in the same coset, and so it looks like this group operation here depends upon which x you choose, but I'm going to show you that if n's a normal subgroup, which is where we started, that's not the case. So let me just pinch that in. So I'm going to specify that nx equals nx dash. So that means x is related to x dash in the sense that they're the same coset. I think we showed earlier that being in the same coset is an equivalence relation. And I'm also going to assume that ny equals ny dash. So we've chosen, here's my coset, I've chosen an x and an x dash and a y, which is that point, this point here, and a y dash in the same coset. And so when we multiply the coset together, it shouldn't matter which element we've picked. It's because it's the coset that's doing the work, not the element. So I have got to show that nx, did I use a little dot for that? Yeah, I did. nx dot ny equals nx dash dot ny dash. It's a better, because these are the same guys. Sorry, that is the same as that. They're equal. The element x is different, but the coset's the same, because I've chosen x and x dash to be in the same coset. And so when we multiply the cosets together, we better get the same answer. And those are equal as well. Alright? Well, let's have a look at this. Let's have a look at what nx circle ny is. Well, by definition, that's nxy. So it's the coset that contains xy. Equals. What does that equal? That equals nx y, which equals xn y. Why? Because n's normal, and if n's normal, the left cosets are equal to the right coset. So I've just swapped it over because that's what a normal coset is, a normal subgroup is. Equals x dash n y. Why is that? That's because I'm specifically requiring nx equals nx dash, because x is related to x dash because they're in the same coset. Equals x dash ny. See how I'm using associativity every step of the way. Equals x dash ny dash, because y and y dash are in the same coset, equals what do I want to do? I want to go x dash n, don't I? Y dash. You see where this is going. Nx dash y dash. What have I done here? I've shown that nx, in fact I'll write it out again, nx ny, which is where we started, is equal to nx dash y dash, which equals, of course, nx dash circle, that should be a circle there, ny dash, QED. So here we've got a nice little way of thinking about the elements of G. We're going to ask which coset's it in. We're going to map the elements of G. Each element x of G is mapped to the coset that contains it. And now we're in a position, no, we're not just in a position, we are all set to define a group operation on the set of cosets here. And then I'm going to show that the kernel of that homomorphism is in fact n. Well, we've done that already. Right, I'm going to stop there.